today I'm going to speak about how we can use X-ray computer tomography or X-ray microscopy to assess or to inspect lithium-ion batteries or other type of batteries. And the motivation for this is, of course, there is a great growth and demand of rechargeable batteries right now for the automotive industry and for other applications in the medical industry and electronics. But NEV is growing so fast that we need to be aware of that and try to address the needs of this market, especially in the inspection side. Now, there is the battery challenge for all the automotive manufacturers, because there are several form factors. There are some battery manufacturers that are trying to do cylindrical cells, and what they are doing is creating packs, large packs of a bunch of those cylindrical cells, and they say this is going to be the optimum way to do it, because if any of those cells fail, they could easily switch off and then continue in operation. But there are other automakers that are following a different philosophy, and battery manufacturers, which they do pouch cells. And we have seen pouch cells as large as a 300 millimeter length or even 600 millimeter length. The width is mostly around 100 millimeters. And there is the prismatic, which is basically a big brick. And there are, I guess, from my point of view, the ones that are pushing the most are the cylindrical cells and the pouch battery. Who is going to win the race at the end of the decade? I don't know. That's interesting to see. And there are several inspection technologies out there to do battery inspection, including ultrasound, visible light, and electron microscopes and X-rays. There are advantages and disadvantages. Some of them, you have to destroy the part, and the resolution is quite limited. Electron microscopy is great, but one of the disadvantages is you have to slice the battery. X-rays is I will say, one of the only technologies that could scan the most variety of scale sizes from the nanometers to the micrometer range. And it's non-destructive, so that's one of the main advantages. And you can see all the type of features that you could scan in batteries, and the type of coverage that you will get in terms of scale. From the several types of technologies that you have in the X-ray, there are several types of different type of systems. There is macro CT, micro CT, there is nano CT, or even synchrotron CT, or other technologies that are out there. I will say for battery inspections, the two boxes show you what are the main technologies: macro CT, micro CT, and nano CT. Depending on what you're looking for, then the type of object size and spatial resolution that you will be able to see. So let me go a little bit more in details on two types of technologies. The first one is the traditional micro CT, which is basically composed of an X-ray source and a flat panel detector. You put the sample. The principle of operation is very simple. It's the same principle of a machine, a CAT scan. When you go to the doctor and they say, we need to do a CAT scan on you to see inside of your bones or anything that is wrong in your body, it's the same principle. We shoot X-rays and we see inside of the battery. And there is a little more elaborate technology, which is called X-ray microscopy, which, in additional to having the geometrical magnification from the CT, has a set of lenses. Those set of lenses allow you to zoom in regions of interest of the battery and see at a higher resolution a portion of that battery. That's why we call it X-ray microscopes, because it has a set of lenses that you can switch from one to the other to get your magnification to resolutions down to 500 nanometers. And to give you an example of what you can do, you could scan the full electronic device like a smartphone and then zoom in a small region of interest, in this case the battery, and see all kind of things that are happening after the several cycles of charging and discharging the battery. You see traces of delamination and particle degradation, which is quite interesting for people that are manufacturing these batteries. And I will show several other examples. This is an example of a cylindrical cell. This is an 18650 lithium-ion battery, and you can see how we can scan the full battery and then zoom in with one of those lenses and see a smaller region of interest without destroying the battery or cutting it, and see a higher spatial resolution. In the image that you see here in grayscale, you see two scans. One at low resolution, which comes from the full battery scan, and then the second one, which is zooming in. And you can see clearly the spatial resolution improvements, such that you can see particle inclusions and some of the separation, some kind of fractures that are going to create a kind of a crack in some of the interlayers. And with some software manipulations, of course, the data mainly is a grayscale, but you could identify by the type of gray different materials, and with a software reconstruction, post-processing, you can assign different type of colors. The main use of these systems in the quality industry is to check for any kind of defects, porosity, particle inclusions, and other modifications of the layers after several cycles of charging and discharging. In this example, you will see how after scanning this with different magnifications, and you will see here each portion that you are seeing here is basically switching those lenses and scanning another region of interest. The sample hasn't been destroyed. Those chunks of battery that you see there is because that's the field of view that we are seeing with the scanner, but the battery is intact. And you can see now some of the quality assessments. You see the bright spots. Those are particle inclusions that are supposed not to be there. And on top of that, if you wait for a couple of more seconds, you will see that we are able to detect a crack inside of the battery. And that's the segmentation of the cracks. So it is a very useful tool for doing a non-destructive analysis assessments of batteries. Let me see if I can show you the workflow. It's summarized here. Basically, you can collect voxel size is kind of a measure of resolution. You can get a general overview of the full battery and then zoom in the different regions until you get 2 micrometer voxel size for the full scan of this region at a higher magnification. The X-rays not only are very useful to see at high spatial resolution, but also at high contrast. And this is something that you can see here, that there are materials of different density, and we are able to identify them. And this is really powerful with the X-ray microscopy. This is something that is typically quite hard with the traditional CAT scan, but the advantage of the technology that we use with a set of scintillators, and on top of that, a set of magnification lenses that go into a CCD detector allows you to do this type of imaging. And this is another example of a workflow for a pouch battery now from a cell phone. You can see that we scan the battery with a full field of view, then a 0.4x, 4x magnification, and a 20x. And you see the increase on spatial resolution and the level of details to a point that you can see the microstructure of the distribution of the particles. And again, you can add segmentation colors to do some manipulation of the data here. And with more software manipulation, you can see some kind of videos to see the segmentation of the data in here. This is also another pouch battery, and you see a section of the battery being slid through in this portion of the battery. In here, what you see is the comparison of two different scans. One is a fresh battery, and another is a battery that has been cycled 200 times. And you can see that in the first one, you can see those bright spots, which is part of the silicon anode, and in the 200 cycles, it has disappeared. And we wonder what happened in the process. So we decided to scan the battery also at 100 cycles, and we can detect how the silicon is being consumed and is generating those cracks and porosity. And this is a scan of the portion of the battery at a higher resolution where that crack was. And you can see how there is the destruction of the particles there. So we saw aging for looking at what happened with some of the manipulation of the particles, but it is also very useful to see how the electrodes are bending. And you see here, after 80 cycles, a battery cell, there are several electrodes in the top that are bending, and they are even touching together. And this is very critical for battery manufacturers to assess. So you can do some physiological studies of the battery. The other topic that is quite important is calendaring. And calendaring is this process in which you put pressure to create these battery packs. And if you put too low of a pressure, then the packing of the microparticles is not really good. You see a lot of spacing, and if you leave spacing between those particles, then the energy density accumulation of the battery cell is very poor. And this is also something important that you would like to check. When you want to do a much higher resolution, you could go all the way down to nanometer resolution, such that you can see details at the particle levels. And you can see some of the particles here have been cracked, and they are split in two or more pieces. And this is also quite important to determine what happened after several cycles of charging and discharging on the type of material that you're using in your batteries. With more advanced software manipulation, you can even create a color segmentation of all the type of batteries, and even do the segmentation of the dendrites. You can take the data that you have in grayscale, and this is really at nanometer resolution, and create some types of simulations, flow simulations, and create some kind of a mechanical simulation that give you idea of how the behavior of the fibers of the porosity in the battery is. I could give you more and more examples, but in reality, what I would prefer is to refer you to some of the publications that are out there. And this is a Nature Communications publication of 2020, in which you can see how you can scan with X-ray CT with 23 micrometers voxel size, and then go all the way to the ultra X-ray microscope at 126 or even 63 nanometers, and see details that are quite similar to an SEM or electron scanning electron microscope. This one is only for comparison, but in reality you have the data in the X-ray CT with 3D data. So you can actually see through the full section of the battery that you are scanning. Another interesting publication that it will be worth for you to check is this one, which is also in Nature Energy, and I think is from around 2020 or 21. So feel free to check that. Most of the conversation that I am presenting today, it's also published in an open access article, and this was published this year. There is a lot of interest, as you can see from the number of views, and it's basically the presentation that I'm giving today with more details on how we do it. You see some of the images and some explanation of the technology, where the technology is in terms of X-ray inspection for batteries. So feel free to check. They're not going to charge you. You just click and it will download the PDF for you. So there are several types of technologies that we can use, and we have most of those at size to check all the way from the battery material to the battery production and do inline and at-line quality control and failure analysis. So you can check the cathode, the anode, the cathode, the separator, the raw material, the electrode production, the cell, the full cell assembly, the module assembly, and even the battery packs. For checking for all of those types of characteristics, like the stacking, the winding, you can check prismatic cells, pouch cells, cylindrical cells, and depending, of course, of the size of the battery, then you will have to check what type of X-ray systems you will need, because it depends a lot of the X-ray penetration path into the materials. For checking more like full assembled batteries, you can check for not only for the battery materials, but also for the assembly, like the aluminum materials or steel materials that you have in the casing. So you can check the collecting tab, you can check some porosity on that, you can check the traditional overhang measurement, the housing, the welding of the final product, the lamination in the battery, deflected anodes, as you can see there, particle inclusions that you are not expecting, the electronic components that are inside of the battery, and any other type of cell defects. So again, this is a full correlative microscopy, I will say. You might need, or you might use different tools, but the idea is that you can assess the battery from the nanometer range all the way to centimeter range. So basically, from the battery materials to the final product or the battery cell or battery pack. The spatial resolutions that can be detected goes all the way from nanometer range to micrometer or millimeter range. And I'm illustrating here a set of tools that you could use. The one that is in the square, in the blue square, is highlighting where the X-ray technologies are in terms of spatial resolution. But certainly you can go down to even half a nanometer if you use an helium-ion microscope. And there are other electron microscopes that you can use. Again, the main advantage of X-ray is that it's non-destructive. At some point, if you use the ultra, you will have to prepare a small sample to get this 50 nanometers, but most of the macroscopics, you can scan the battery without destroying it. And if you want to do higher spatial resolution assessments, then you can send that to an electron microscope and do the correlation. There are other kind of tools. It's not, when you are inspecting batteries, it's not only assessing the microscopy part, but there are other types of inspections when you have the final product of the battery pack, and you can inspect that with some optical tools or even coordinate measuring machines to see that the dimensions of those battery packs are correct. So you can use some laser scanning or some coordinate measurement or CMM. So we have a full portfolio that could offer or solve different needs for you, not only in the battery space, in all types of industries, but of course this is a battery conference, so that's why I am particularly focusing on batteries. So the applications in battery manufacturing go from the laboratory and at line. So you can go in the full cycle from the R&D to at production or the quality lab and do failure analysis. So you can close the full battery cycle. Oh, sorry, just checking timing. Let me go one back. So you can close the full cycle of a battery creation with all those types of tools, not only X-ray microscopy, but also electron microscopy or optical scanners. And it is with pride that we like to announce that we started some partnership with the University of Michigan. The University of Michigan, the battery lab. The battery lab is, that we have in Michigan, in the University of Michigan, is very unique. It's a campus research core in Ann Arbor that allows to do some academic investigation, but is mainly focused with industrial users. So we have, or they have, partnership with most of the battery manufacturers and car manufacturers around the area and the country. And since we offer, I will say, the largest portfolio in industrial quality and research inspection for batteries, we recently entered a cooperation, and we're going to continue work together to not only serve current manufacturers, but also to lead where the battery goes in the future. There's a lot of advance in battery manufacturing. Today, we don't know where this industry is going in 5, 10 years from now, 20 years from now. So we are keeping a close eye in the evolution of the batteries so we can provide the right solutions for battery quality inspection. And I think that is the last slide that I wanted to present. We have a booth which we welcome you to come. It's the booth 801, and you will find all kind of experts there that could talk to you and show you more of the tools that we have. There are some microscopes and some X-ray CT models there, so you get an idea. You can also contact me by email and send me a messenger. With this, I think I'm gonna give room for questions if you have. Just wait for the mic. Where is Rob?
So, hello? Oh my God, I'm sorry. So I might have missed it because I came in a little late, but what are the chances this can be automated in the future, since it's going to be quality for every battery on the line?
Yes, that's a very important question. And yes, it is possible to do some type of, I would say, at the moment, semi-automation, not fully automation. Possible full automation in the future. The main challenge that we have, at least in X-ray technology, is the scanning time. The scanning times can go from something in the order of minutes to in the order of hours, depending on the resolution that you're looking for. And as I understand, when you're doing battery manufacturing, you're just creating several batteries per minute. So probably an assessment of at that speed is not possible, but it's possible to do some type of sampling. And the other challenge that you will have is the cabinet is operating with X-rays. So it needs to be protected to the outside for the operator. So it needs to have some type of a robot that kind of load and download the battery. So that is possible. There is a trade-off between speed and resolution. When you increase the speed, it means that you have to do a very quick scan, which is not the highest quality, and then the resolution is in the order of 100 microns or so. If you want to go down to nanometer resolution, then you have to spend more time. probably in the order of 1 hour or more. There are other possibilities which could be quicker, which is not doing full CT scan and is doing 2D X-ray, and because you only need to shot once, but the assessments that you could do are limited. And those are assessments like overhang, for example, because it's basically looking at the electrodes, how they differentiate one from the other in terms of height. And you can easily see that in an X-ray image. So you can use a 2D detector, and that actually could be implemented in line. You're welcome. Yes, please.
Yeah, so I guess my question goes along a little bit with hers. You mentioned some size limitations in the sample.
Yes.
So if that were to be automated, I'm guessing you want to look at a full battery. So what sort of sizes are you limited to?
Yeah, so let me explain a little bit of how the physics of X-rays work so we can understand the size limitation. When you shoot X-rays through a sample, the X-rays penetrate the sample and they pass across, and then you have a detector. And what the detector sees on the other sides is the transmission of the initial signal. And there is an attenuation of the signal. So there is an exponential attenuation, which means that what you see on the other side is going to go decaying. And there are two terms that drive that exponential curve. One is the thickness of the sample, and the second one is the density of the sample. So if you have very high atomic number elements, then the penetration is shorter. And if you have thicker samples, then the signal that you see in the other side is less. So what you have to do? You have to change the power of the X-ray source. It's typical traditional X-ray CT systems for industry are operated at 225 kV. And that can give you fairly good images with the cylindrical cells, even the 2880, and probably the 400 series that is going to be released or was released in the market. If you want to do now higher batteries like the prismatic batteries, then probably you need to use a 320 kV source or a 450 kV. So you increase the X-ray source. There are trade-offs. When you increase the X-ray source, then there is the chance that you are decreasing the resolution. So you have to play with those two factors. I will say, if you use high kV systems, it's great for general assembly in terms of how the battery is inside and maybe some overhang, but you will not be able to see at the particle level. To do that, you need to use a smaller sample and then use 160 kV with optical magnifications that give you that higher resolution. So it's basically a play game with the different limitations of the physics of X-rays and the size and material of the sample. Any other questions? I think we have plenty of time. If you have more, please go ahead.
Hi. Thanks for the presentation. So, using the scan, can you determine how much life is in the battery using a CT scan? Mm-hmm. You talk about aging.
Yeah. So what I have seen that the battery manufacturers are doing is they put the battery through these cycling periods, and then they scan the sample when it was fresh, and then they scan a certain cycles. So let's say they create a battery that goes 500 cycles. So they create the battery and then they discharge, let's say 20 cycles, 40 cycles, 80 cycles, and they can see how the battery is changing over the cycling time. And that is giving them an idea of how the the internal composition of the anode or the electrodes is degrading, and that can, if they do that, and I'm not a battery expert, but they have their own models, they could predict how much the battery could last and can still be used. So that's the main idea. You cannot predict how much the battery is gonna last with just doing a scan of a fresh battery, because it's gonna give you everything is pretty and beauty. So you have to do the experiment. Yeah. And it would be ideal in the X-ray technology to have some kind of in situ testing in which you do the charging and discharging of the battery inside, so you don't have to take it out and do the charging. We're working on some of that technology to enable to do the full charging and discharging inside of the X-ray CT scanner. All right. Any other questions for today? Going once? Yes, please. Just wait.
Once again, I may have just missed this, but is there a way to go through and sequence it through the X-ray, then CTE, then like going through an actual train of testing? Does that make sense?
Can you explain maybe a little better?
So can you do like repeatability? Like you were saying it degrades. If you wanted to say put it in a specific condition and bring it back, can you just save the sequencing or save the specific parameters that you wanted from that test?
Of course. You can save the parameters that you are using for the scanning and then use it in the next one. So that's kind of the easiest way to do it, because once you do one, you know how to do the other in terms of optimization. There are several parameters that are important when you are scanning batteries, and those include the X-ray kV that you use. When I mentioned that there are 225 kV systems out there, it doesn't mean that people use it at 225. It goes all the way from maybe 20 kV to 225. So you have to find what is the optimal parameters to optimize the signal to noise ratio. Then you have to optimize the time to see how much exposure you need to do in the detector. And once you have that recipe, you can apply it to the next ones. The challenge is when you come from a battery that is totally different, then you have to start again with the optimization. But in principle, an experienced operator should know how to do this after a couple of weeks of training that learn how to operate this technology.
That actually led to another question, if I can. So that actually brings up another one for me. Do we have to zero this every once in a while to make sure that it's standardized each time? So for instance, a lot of instruments can have heating over time, and that can cause issues with the testing. Yep. So do we have to zero it after so many tests? And if so, do you know how long that is?
I will say it depends on the manufacturer you buy the system with. So you need to be very careful when you try to acquire one of those X-ray CT systems. Really investigate who you're buying from. I will say from the side systems, we have designed a way to make the systems stable. And I will say from the X-ray microscopes, they could do scan times 24 hours long or more with no issues of stability. There is a setting inside of the system that automatically detects when it has to relax the focal spot of the machine or something like that. The issue of temperature, though, is an important one, because when you see the physics of conversions of electrons hitting into a target and then creating X-rays, most of the energy conversion goes into heating. So you need to have a cooling system that maintains these refrigerations into the system. I will say the most concern It's with the traditional flat panel detectors. Sometimes, depending on the manufacturers, it might have issues if you try to do more than 3 hours scan. We have designed a technology such that you don't have to worry about that. There are other things that you have to check from time to time, which is consumables, which is the filament. After certain hundreds of hours, you have to change it. But also there are different approaches out there. There are people that recommend that you change the filament. There are other people that just have a filament that lasts for longer. Or there are open tubes and closed tubes. X-ray microscopes have closed tubes where you don't have to do this type of filament change because it's in a high vacuum and it lasts for years. Yes, at some point you will have to change the X-ray source, but you don't have to worry about interrupting your operation in your manufacturing or in your inspection. You're welcome.
Done.
All right. Anyone else that is not the person that... I do appreciate your questions. Okay, so enjoy the show, and if you want to stop by the booth, welcome. We'll be there until Thursday.